Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over a problem on comparing different gases in different size boxes at the same temperature and comparing pressure, density, kinetic energy, and things like that. So let's get into this. So in this problem we're asked to consider the following pictures of gases right here. So we've got these pictures of gases and they're all at the same temperature. That's going to be very important. So same temperature. And you can see that in the different boxes, we have different kinds of particles. And we're told that the white circle or the white dot or ball here is the neon. And the black dot here is argon. And so that's going to be important too. In just a moment, I'll explain. So they want us to arrange each of these pictures in order from lowest to highest according to what characteristic they want us to look at. So we're going to order the boxes according to pressure, lowest to highest, according to average kinetic energy, lowest to highest, density, lowest to highest, and root mean square speed or velocity, lowest to highest. And so we're going to do that. But first, they tell us to assume that large boxes are twice as big as the small ones. Now, my pictures are probably not drawn perfectly to scale, but the idea is that the difference between the small and large boxes is a factor of 2. So the large boxes are supposed to be exactly double the size of the small boxes. And of course, the small boxes are going to be equal to each other. The large boxes are going to be equal to each other. But the small and the large differ by a factor of 2, small being half the size of the large being twice as big as the small. Okay, so that's one assumption we ought to make. And they're asking us to approximate the masses of neon and argon to 2 sig figs. So let's go ahead and do that. So if we look up neon on the periodic table that I have here, neon has a mass of 20.18. So we'll round that. So neon is just going to be 20, right? So grams per, or we could say AMU for atomic mass units, or grams per mole for molar mass, right? So AMU. And if we look at argon, which is just below neon, that's going to be 39.95, but we want to round that to 2 sig figs. So 39.95 is going to be 40. So argon is equal to 40 AMU, or 40 grams per mole. Now, notice here that neon is twice as small as the argon. So argon is twice as heavy as neon. And so that's going to be important. Notice that they're twice. And the boxes here are twice. They differ by a factor of 2. The masses here differ by a factor of 2. So that's going to be important for ordering according to these particular characteristics or characters. Okay, so let's go ahead and do this. So they want us to do pressure. So pressure, notice that this is at constant, same temperature. So if they're all at the same temperature, then they're going to move around at the same speed pretty much. Well, not the same speed, but the average kinetic energy. So remember, pressure in this case, if temperature is the same, then pressure does not depend on the kind of particle you have. Doesn't depend on the mass of the particle. It doesn't depend on what particles they are. It doesn't depend on the identity of the particles. It just depends on the size of the box it's in and how many particles you have, right? The more particles you have, pressure goes up. The smaller the box, pressure goes up, right? All things being equal. So we want to go from the lowest pressure to the highest pressure. So that means that pressure is going to be lowest when the box is largest and you have the fewest amount of particles. Why can I say that? So if I write down here, remember that pressure is equal to force over area. What's causing the force in the box? The collisions of the particles against the sides of the box, right? So that's going to be the force. So how many particles you have is going to be a greater amount of force. So that's going to be related to number of particles. Okay? And then the area here is related to the surface area on the inside of the box, which is going to be related to the volume. Larger volume means more surface area on the inside of the box. So this is going to be related to volume of the box. Okay, so pressure is going to be the lowest when the numerator is smallest and the denominator is largest. So we're looking for the box with largest volume, lowest number of particles. And so if we look here, right, which one's largest? Oh, I forgot to mention, note, I forgot the note. So in some cases, the pictures may be equal in raking. So we may have equal boxes. And so if you look here, I have a large box with 3 particles. So we want the largest volume, right? So we want to look at the largest volumes here. So these 4, largest volume, and number of particles is the lowest. So out of these 4 boxes that have the largest volume, which ones have the lowest number of particles? It would be these 2 here. They both have 3. So these 2 would be the lowest pressure, and they're going to be equal to each other because they have the same volume, same number of particles. So then that means pressure, the ranking would be starting with number 1 and number 5. So number 1 is going to be equal to number 5. That's the lowest. So what's next? Okay, so next, again, it's going to be either increasing the particles or decreasing the volume, right, or both. So we're going to see what's the greatest. So let's look at what's the greatest here. So the greatest pressure would be due to the greatest amount of particles and the lowest volume, right? The smallest volume, greatest number of particles. So we want the greatest number of particles, smallest volume. Well, the smallest volume is going to be these 4 boxes here. They're all equal in size, equal in volume. So then out of these 4, the greatest number of particles, which is the other factor, is going to be the next one. So out of these 3 volume or the 4 boxes, which one has the greatest number of particles is going to be these 2 here. They have the greatest number of particles. Now, we'll order these in a moment. But what about in between? So notice here that I go from 1 and 5. If I go from here to here, I am decreasing the volume but keeping the particles the same, right? So if I decrease the volume here, but the particles are the same, I'm decreasing the volume. So that means pressure is going to go up. So this is going to have a higher pressure. And this is the same. So this will have a higher pressure too. These are going to be equal in pressure because they have the same volume, same number of particles. So both of these are going to have a higher pressure than these 2. Now, what about these 2 here? So if you pay attention to this one and this one, notice that the box here has doubled in size. But notice also that the number of particles has doubled in size. So if we look here, volume has been doubled and the number of particles has been doubled, right? So if we double this, right, if we multiply this by 2, the volume is doubled, and we multiply the particles by 2, and that's doubled, then notice what happens to the 2 and 2. They cancel out, which means that you have the same pressure as before. So this box is going to have the same pressure as this one because at the same time we doubled the volume, but we also doubled the number of particles. So the pressure stays the same. So the ratio of volume to particles is the same as for these 2. And then also, if these 2 have the same pressure, right? And this box is the same relationship, right? So going from this box to this box, number 7, we doubled the volume and we doubled the number of particles in the box. So again, the pressure in this box should be the same as the pressure in this box because they cancel each other out. Doubling the volume and doubling the number of particles keeps the ratio the same, so it's the same pressure. So in this case, all 4 of these boxes here have the same pressure. So then here we'll have 2 is equal, the pressure in 2 is equal to the pressure in 3, which is equal to the pressure in 6, and which is equal to the pressure in 7. Okay, so those 4 boxes are equal to each other. And then as we said before, these 2 boxes have the highest pressure because they have the highest number of particles, numerator, and they have the smallest volume, denominator. And so both of these are the same. They have the same volume, same number of particles. So the pressures of these are going to be equal and they're going to be the greatest. So here the pressure in number 4 is equal to the pressure in number 8. And so that's how you order the boxes according to pressure. Okay, so let's go to the next one. Okay, next we have average kinetic energy. So they're asking us to order each of the boxes, arrange these are the boxes in order from lowest to highest according to average kinetic energy. Here's the thing though, we're told that all the gases in the boxes have the same temperature. The temperature is a measure of the average kinetic energy. So if all boxes are at the same temperature, then all boxes have the same average kinetic energy. So this is kind of a trick question. So this was testing you on whether you know that temperature is a measurement of the average kinetic energy of the particles in the box. And it's an average because, remember, not all particles are moving at the same speeds, right? They all have the same masses, where if we're talking about the same particles, same type of particles. And so, but it's an average because, we're averaging them together. So it's an average. So in this case, the answer to this is they are all equal. So they all have the same average kinetic energy. Okay, now what about density? So density, same thing as pressure, right? So if we look at density, so what's density? Density is equal to the mass over the volume. So mass per volume. Okay, so here we got to consider the mass of the particles and the number of the particles. So the number of particles and the mass of the particles are going to be important for the mass part of this, and the volume is going to be the volume of the boxes. So they want to start order from lowest. So what's going to have the lowest density? Lowest density is going to be highest volume, least mass. Least mass, and again, let me specify this. Least mass is going to be related to number and kind. Why number and kind? Because remember, we have 2 different particles, neon and argon. Neon is 20, argon is 40. Argon particles are going to be more massive. So if you have 3 argon particles in a box and you have 3 neon particles in a box, the argon particles are heavier, so it's going to be more dense, assuming that the boxes are equal in volume. Okay, so what is going to have the greatest mass and the largest volume? It's going to be the least mass and the greatest volume, right? So least mass, greatest volume, that's going to be the least dense. So least mass, greatest volume. and that would be, well, if we're looking for the least mass, that's going to be the number and type. So these two have the least mass, and they got the least number. So this has, because remember, neon here, this is neon. So we have 3 neon particles. Here, this is argon. That's going to be greater mass. So we're going to ignore the dark ones first, and we're going to look at the light ones here. So we have 3 here, and we have 3 here. So these two are equal in the amount of mass. What about the volume? Well, which one has a greater volume? The one with the greater volume is going to have less density. And so this one has the greater volume and it has less mass. So this one, number 1, is the least dense. So number 1 is going to be the least dense. Okay, so now what's next? So if we look at this one, if we decrease the volume here, then number 2 is going to be more dense than number 3, right? So decreasing the volume, we're going to half the volume, so therefore the density is doubled, right? So this is going to be more dense. And then what about this one here, right? So if we look at number 3, notice that number 3 and number 2 have the same type of particles. So these are neon. Notice at 3, you're going to double the volume. But notice you also double the number and kind, right? The same kind of particles. You're going to double the number of particles. So if you double the number of particles and you double the volume, they're going to have the same density. How do I know that? Let's see here. So here, mass, I'm going to double the number of particles. But they're the same in kind. So I double the number of particles and then I double the volume. So then the 2's cancel out. I end up with the same ratio, right? So same density. So 2 and 3 are going to have the same density, okay? Now, what about the others? So let's look at number 5 here, right? So here I have doubled the volume, right? So I went from here to here. I'm doubling the volume. But notice that I have the same number of particles. So the same number of particles is going to be the same. That's redundant. The particles, the number of the particles are the same. So here I have 3 of the neon. Here I have 3 of the argon. But notice that argon is twice as big. So even though the number is the same, I have increased the mass by double, right? So each of these argon particles is double the mass of each of these 3. The numbers are the same, so the mass is doubled. But as we said before, I double the volume, I double the mass. The difference between this and this is that here I doubled the volume and I doubled the number of particles. So because I doubled the number of particles, but the masses are the same, I doubled the mass. Here, I kept the number of particles the same, but I doubled the mass of each of the particles. So overall, the mass is doubled. So this one and this one have the same density. This one and this one has the same density as well. And so these 3, 2, 3, and 5 are going to have the same density. So 2 is equal to 3 is going to be equal to 5 in density. Now, the other boxes here, this has more particles but less dense. So this one is going to be more dense than that one. So that's not going to be in this group. This one has a smaller volume than this one. So this one's going to be more dense. So that's not going to be in the same group. So all of these are not going to be equal for that reason, because they either have too many particles or they have less volume. Okay, So what's next? So here we have this one, right? So going from this one to this one, we have a greater volume, right? But we also have more particles, right? So we increased the volume, but we also increased the number of particles. So that one's going to be more dense. But here, okay, let's look at this one also. So number 6, like I said, if we're comparing this and this one is going to be twice as dense than this one. They have the same number of particles, but the volume has been cut in half. So we decrease the volume by 2, and so the density is going to be increased. So this one has more increase. Let me go ahead and erase this. So the density is going to be double. So if I half the volume, right, dividing by half is the same as multiplying by 2. So I multiply mass by 2. So this whole thing, the whole fraction is multiplied by 2. So it's doubling the density. Okay, so this density is doubled than this one. Okay, so what about this one? Notice here that I doubled the number of particles, but the particles are the same type. So I've doubled the mass here, but I've also doubled the volume. So again, I've doubled the mass because I've doubled the number of particles of the same kind, and I doubled the volume, so the density is the same. So this one is going to be greater than 5. So that means if this one and this one is equal, then this one's going to be greater than 5. So these two are equal. And then what about number 4? Here you can see that the number of particles here is 6, but they're 6 here. But notice that the mass is half, right? So I have the same number of particles here and here, but here I have neon, which is half the mass. So because I have the same particles, I'm cutting the mass in half when I go from here to here, right? But I'm also cutting the volume in half. So in this case, right, I'm cutting the mass in half and I'm cutting the volume in half. So the halves cancel out. So I get the same ratio, same density. So number 4 has the same density as number 7, which also has the same density as number 6. So those are all equal. So number 6 is equal to number 7, which is also equal to number 4. Oops. Number 4. Okay, now that leaves one box left, number 8. That must be the most dense, but let's just check it out. So here, number 8 has the least volume, the greatest number of particles, and they're the heaviest. So out of all of the boxes, this is going to be the most dense. So that's going to be the last one, number 8. Okay. Last one, root mean square speed. Now, this again is related to the temperature, but also we don't want to confuse this with average kinetic energy. Remember, kinetic energy is the 1/2 mv squared. So let me write that down. So kinetic energy, or I should say average kinetic energy, is equal to 1/2 times the mass times the average velocity squared. So here the mass and the velocities are going to balance each other out. So higher mass, the more massive a particle is, the slower it's going to go, right? So you could have a more massive particle moving at a smaller speed, and then compare that to a less massive particle moving at a higher speed, and the mass and the speed are going to kind of cancel each other out, or they're going to balance out. So you can have two gases of different particles at the same temperature, and the average speed of the lighter particle is going to be less massive, so the mass is going to be lower. The average speed is going to be higher, so they kind of balance out. So you end up getting the same average kinetic energy for any particle. So this is why the identity of the particles doesn't matter when you're talking about kinetic energy. However, when you're talking about the root mean square velocity or speed, that does matter as far as the type of particle because of the relationship between the mass and the speed. So here we're only looking at the velocity here, the average velocity. That's what root mean square velocity is. We're looking at kind of the average here. We're ignoring the mass, right? So what I just said was lighter particles are going to be moving faster than heavier particles on average, right? So lighter particles are going to have a faster average velocity, root mean square velocity, than the heavier particles are going to have. Now, this does not depend on volume. It doesn't depend on the number of particles. It just depends on temperature, right? So if all particles are at the same temperature, then the only thing determining whether or not something's moving faster, whatever the average velocity is going to be the mass of the particles. So here, all of these boxes have lighter particles. They have different volumes, different number of particles, but that doesn't affect what the average speed is going to be of the particles. So I can throw more particles in there. It's not going to affect the average speed, right? That is going to be determined by temperature. And so here, since the temperature is the same, the only thing that's going to be a difference in the average speed is the mass of the particles. So since all three of these have a smaller mass, they have smaller mass particles, they're all going to be have a root mean square velocity that's going to be the same, since they're all the same type of particle. So here, the root mean square velocity, all 1, 2, 3, 4 are equal. So 1 is equal to 2, which is equal to 3, which is equal to 4. Oops, I was going to put 5 there, not 5. 4. And they all have a, we're supposed to do lowest to highest, so lowest. So the heavier particles are going to be slower because they're heavier, right? So these 5, 6, 7, and 8 are going to be slower, lower root mean square speed compared to these 4. So I was going to write it backwards, but I caught myself. So 5 is equal to 6, which is equal to 7, which is equal to 8. And then these are going to have a lower root mean square speed compared to these 4 boxes here. So 1 is going to be equal to 2, which is going to be equal to 3, which is going to be equal to 4. And that, ladies and gentlemen, is how you answer this question. That's how you do it. I hope you enjoyed this video. If this was helpful in any way, then please, by all means, like the video, share the video, hit that like button. Also, make sure you do me a favor, do me a solid here. Subscribe to my channel, hit that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem that you need help with, let me know. If you have a topic you want me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.